Hashing. What is hashing? Hashing is a data structure which has a hash function in between. It stores key value pairs. When you pass the key to our hash function, we get a hash value, and with respect to that hash value, we store the value in our hash table. Here we are using arrays, so instead of calling hash values, we say indexes, and for the indexes, we store the values. So this is a collision resolution technique. So this was about hashing. Now there are different types of collision resolution techniques, like linear probing in hashing. Let's say we have keys here and a hash function. If we occurred a collision, what we do is we simply go to our next position, which is empty, and then we store our element over there. Simply search for the next empty index from the original index. That was linear probing. Now there is another technique, that is quadratic probing. In quadratic probing, what happens is we use a hash function, and if we occur any collisions, what we do is we simply take the hash of that, we square it, we add one, and then we move to that position. And if that position is full again, we take again the hash, we square it, add it, and again we move to the next position. If it is full again, we square it, add it, and move to the next position. So this was about quadratic probing. Now there is another technique, that is double hashing. In double hashing, what happens is double hashing is a collision resolution technique also. So in double hashing, we use two functions. That is hash of 1 and hash 2. Now here the first function is used to determine the hash value in our table. Let's say we occurred a collision. Then what we do, we move on to our what next hash, which defines the probing. Now what is probing? Probing is um, how much space do we need to leave before what moving to our next empty space. You'll understand when I'll start with an example. Let's say insert 18, and let's say my function is k modulo 13. When I try to insert 18, 18 modulo 13 is what? 5. So I'll go over here and I'll insert 18 over here. Okay, getting you guys following up?
Yes.
Uh, so when I want to insert 41, I'll simply go over here, that is h1 of k, and 41 modulo 13, that is what? 2. I'll simply uh, insert 41 over here. Then if I want to insert 22, what I do, I'll simply go over here. I'll go over here, that is 22 mod 13. That is what? Here, 22. Now, 44. I go over here, 44. 44 mod 13. What is it? What is 44 mod 13? It's 5. 44 mod 13 is 5. We occurred our first collision.
Yes.
So, how do we resolve this collision? We simply go to our next hash function. We say, now we take here 7. I took 7 because it is a prime number. We could take any prime number, like we could take 5, 3, 2, doesn't matter. But usually the prime number which we take over here, that is prime number minus k of modulo prime number. So prime number which we will take is generally less than or equal to our hash table. Okay. So I go to my next hash function here, 7 minus 44 modulo 7 is 2, 7 minus 2, 5 again. So what is this 5? This 5 does not mean that we have to store our element in 5. This 5 means that we have to move 5 boxes, 5 buckets ahead from our position. Getting my point? Now here, when I moved 44 to hash of k modulo 13 was what? 5. This hash function told me that I have to store my element in index 5. But this hash function said me that I have to probe 5 steps ahead of my index. So what I did is I moved 5 steps ahead. One, 2, 3, 4, 5. And I stored my value over here. Getting my point? What is happening?
Yes.
So by this what happens is they are very minimal collisions. And like in linear probing, we do not encounter clusters. Let's say a lot of elements are present. Then we do not encounter clusters in this because we are randomly assigning it somewhere else. Okay. And each element depends on what second hash function, and the probe for each element differs. Let's say 59 mod, what 59 mod 13 is, let's say assume 2. Okay, it's not 2 actually, but let's assume 2. If it is what? So if 59 modulo 2, 59 modulo 13 is 2, then what happens is we encounter a collision. And when we encounter a collision, we move to our second hash function. 7 minus 59 modulo 7. So let's say this is what? This is 4. Then 7 minus 4 will be 3. So what we do, we do not store it in index 3. What we do is we move 3 steps ahead. That is 1, 2, and 3. So here what happened is we have another element. So what we do is we simply move ahead again 3 times. 1, 2, 3, and we store it over here. Getting my point? What is happening?
Mm.
So, for 44, what happened is we have the probe 5. We moved 5 steps. And if here element was present, then we moved another 5 steps. Now here the table is ending. So here our table is not ending. Actually, we are implementing this in a circular manner. Okay. So if I move 5 steps from here, that is 1, 2, 3, 4, 5, I still have an element. So what I do is I move again 5 steps forward. 1, 2, 3, 4, 5, and I store it over here in the hash value 7. That is in the index 7. Now this is how double hashing works actually. This is a very clever way of solving our solution resolution technique. Okay. Uh, Next, 59 mod 13. It's nothing but what? It's 3. So 59 will go over here. So this was it about double hashing. You guys understood, I guess. Did you guys
Yes.
understand? Yeah. Now let's go to insert. How do we insert double hashing? Let's understand it using code. So I included a function and directly moved to the function. Double hash insert. I passed the key and I called my function 1, h1. I called my function for h2. Called my function 2 and I passed my key. Now we usually do not need h2, but for some cases like collision, we need h2. Say for I equals 0, I less than table size, I plus plus, where we are just using a for loop over here to iterate for our probe. Okay, so idx equals, so this is our first hash. Okay, so index is nothing but what our hash value, h1 plus I star hash 2 divided by modulo table size. We're just making things a little hard for different people to, so that our hash table encounters very less collisions. So it depends on your hash functions that your collisions may occur or not. If your hash function is very weak, then you may encounter lot of collisions. Or let's say you may encounter what? See, for example, what happened is here we had an empty space. So sometimes what would happen is we would be stuck in a loop. Like for example, they are empty space over here. But when I went over here, I probed five times. Here an element is present. Then I probe five times. Element is present. I probe five times. Element is present. And after some time, I return to the same position. So what happened is we are stuck in a loop. There are some empty spaces in between. But while we are probing, the elements are filled. So only certain elements are filled at certain indexes, and we are probing through that indexes only. But in reality, what is happening is there are what spaces left inside our hash table which are empty. So it depends on your hash function and your key values. So if your hash function is good enough, then you may encounter very less what collisions or very less what loopings. Okay, so one of the major factor is what your hash functions. So here if hash table index equals empty, that is if my index equals empty or if my index is deleted. So here also we use what? We use our deletion marker. Like let's say I want to search 44, but before searching 44, I have already deleted 18. So when I try to search 44, I go to index 5, but here the element is deleted. So what I return is I return 44 element not found. But in reality, what is happening? 44 is present over here. So what I do is I keep my deleted marker over here. That is what a Tom store. So that I know that there was an element present over here previously, and then I could just probe. I could just go to my second function and take my probe and probe it so that I could find the value. Okay. Now what is happening is if our if our hash table is empty or if our hash table is deleted, then hash table equals key, that index equals key. Now usually what is happening over here is, see in our like previous here what we did, we passed the key and we stored some other value. So here key and value are totally different. But in double hashing what we do is we usually store our key only. That is what we can store our value also, but we are usually storing our keys. That is, our keys are my values itself. Getting my point? You guys following up?
Yes.
So our hash table index equals key. We are what? We are assigning our hash table index equals key if it is empty or if it is deleted. Okay. That is what the statement wants to say is uh, here here my what I want to insert 44. Okay, and here my 18 was element present, but I deleted it. So what I did is I placed my marker over here. That is what deletion marker. Now, if I pass it through hash 1, I go over here, I see a deletion marker. When I see a deletion marker, I do not simply say it is what full. I remove that deletion marker and I place my 44 over here itself. So that is what it's trying to say. If I find a deletion marker or if I find it empty, I'm going to place my key over that index and I'm going to return true because we are using a return type true. That is what our insertion was successful. Or what I'd do is I'd check if our key is what? If our key is index. And if it is not, then I would return false because it is what already present. See, what happened is I wanted to insert what 18 over here. So I moved over here, hash function, and I moved over here. So here what? It is already filled, but I wanted to insert 18. Here we already have what? 18. So what I'll do is I'll check whether my 18 is equal to my index. That is what hash. If it is equal, that is what, if our key is equal, then what I'll do is I'll simply return false because our insertion was not successful. But we know that our key is already present. So we could write just a print statement over that key is already present. Okay. So this was it about inserting in double hashing. So inserting and deletion in double hashing is far more easier than quadratic hashing and okay, quadratic hashing. Linear probing is also almost easy. And if all this fails, then we simply return false. Okay. So that was about what? Uh, that was about inserting and double hashing. Now let's say searching in double hashing. So what we do? We assign our values. It's the same way. Okay. It's oh, the both are same. We encountered a problem. Okay, no, never mind. What I'll do is I'll try to explain from here only. So what we'll do is we can use a while loop, and we could say we could use what two statements, two conditions. If our element is empty, or if our element is what deleted. Uh, Actually, if our element is empty or if our element is found, what we could return our element found. Okay, we could use a while loop over here. And when I pass, let's say I want to search this 44. Now what I do is I pass my value to this hash function 1, and then I move to here, what where I move to this k1. Now here I could simply add an if statement. If my element equals to my key, then I would just return this value and I would return true because we are going to use boolean, of course. And I would print my statement there itself in that function. So I would return true over here. But if it failed, I could use simply an else statement and I could just what? I could call my second function. When I am using my else statement, I'm calling my second function. And when I'm calling my second function, then I'll find my probe. And when I found my probe, I'll simply what? I'll move 5 steps forward. That is, we have 5 steps over here. I'll move probe steps forward and I'll check it again. See, if my element is equals to my key, then I would simply return this, and if not, I would what increment it again for 5 steps forward. So if I move 5 steps forward, if I found it again, then it's simply what I'm using a loop and an if statement. If it is present, then return. If not, then move forward. If it is present, we could use what while loop because we don't know how many times we have to iterate it. Okay, so this is how you search an element in and what double hashing. Getting my point?
Yes.
So this was it about hashing. Now this completes our hashing, not fully because there are various types of hashings. These are only some of the basic types of hashings. That is what linear probing. We what we solved. We occurred collisions. Then we tried to resolve it using what separate chaining and what open addressing. In separate chaining, what happened is we used linked list, we attached it directly to our buckets. In our open addressing, what happened is we use different types of techniques, probing techniques like linear, quadratic, and double hashing. So this was it about some collision resolution techniques. Now let's move to trees. Introduction to trees. So today we are just going to talk about introduction part, and I guess today's class will be over in next 5 minutes. Okay. After that, from tomorrow, we'll start from trees. Okay. Tree data structure. Tree is a non-linear data structure. So the very first point we have to remember is tree is a non-linear data structure. Okay. So tree is like a what? A family tree. You could just call this as family tree. The same thing which we used to do in our what lower classes. That is, we used to do our family tree. We used to draw a tree, we used to write my father, mother, then we used to draw two lines and we used to write brother, sister, grandfather, grandmother, representing how my family tree is. So this is my ancestor. Let's say we call this a root, and this is present at level 0. Okay, so A, B, C, D, E, F, all these are what? All these are what? You could call characters, numbers, anything. You could store anything over here. Okay, it doesn't really matter. Okay, so this is my what? This is my root. We call all this as what? Nodes. So what will this become? This will be my root node. Okay, so from my root node, I have what? Children. That is B and C. So B and C are children to A, and A is what? Parent to B and C. A is ancestor to I and J. Why is A ancestor? Because I's parent is D, D's parent is B, B's parent is A. So A is ancestor to A and J. Also K and L. Also F, G, H. Okay. Instead of ancestor for F, G, H, it is what? Like a grandfather, a grandmother, anything. Okay. So here B, C are what? B, C are children to this A. So the first very top node which is present is root node, and the very bottom nodes like L, K, J, and I. What are they all? They are leaf nodes. Getting my point? So, uh,
Yes.
like a real tree, what happened is in real tree we go bottom top. Here the same way we are going top to bottom, but we are representing in a bottom top manner. So the highest element in a tree is what? Leaf, but the lowest element in a tree is what? Root. So without our root, our tree does not grow. That is what is happening. Without our root, our tree does not grow. And all these last elements or these last nodes are what? Leaves. So this is a tree. And let's say this from B like this. Or you could simply from here Dij. What is this? This is a sub tree. This is what? This is a sub tree. This is a sub tree. Or this EK is also a sub tree. So there may be one or more than one sub trees in a tree. Okay, getting my point. So here D and E are what? Parent to B. Okay, and D and E are actually not parent, actually child to B. And B is parent to D and E. Okay, so from here what we concluded, our node may be child or may be parent. It doesn't really matter. So it is child to A, but it is parent to D and E. Getting my point?
Hmm.
So our node is what it is. It may be parent, it may be child, it doesn't really matter. Okay, and here our B and C are what? Siblings. Because they are from the same what? Same node. So B and C are siblings. The same way F, G, H are also siblings. The same way I, J are also siblings. But we cannot say I and K are siblings because they belong to what? Different nodes. Okay. The same way we cannot say K and L are siblings because they belong to what? Different parents. So a tree may consist of two or more than two nodes. That is what I'm representing over here. It doesn't really matter how many nodes you keep or what you do. But to make things easier for us, what we do is we implement different types of trees. One among them are binary trees. So what you guys will be doing is you guys will be learning a little introduction part about binary trees. Okay, just a little bit introduction. Okay, so that you could understand more better and you guys would not Google anything or not do anything, and you guys would say me, how do I implement this? Like, what data structure should I choose for this representation? Let's say, answer me now that now here this tree looks good, but I want to implement it in my code. So what data structure should I use to implement this code? Should I use arrays? Should I use linked list? Should I use tags, queues, hashing? What should I use to this? What should I use? What would be your very common approach, or what would be your approach on representing these trees in my code? What would be your approach? Any idea?
I think so. Linked list.
Yeah, exactly. We are using what? Doubly linked list. Getting my point over here? So here, instead of representing it to previous and next node, what you are doing is we represent it by right node and left node. That is simply because our nodes are two. And if it is more than two, also we could use what? We could use our doubly linked list only. We could store our data and we could store our pointers over there. And for pointers, we could say this is node 1, node 2, node 3, node 4. That is node pointer 1, node pointer 2. And like here, for C, what we have our what parent pointer to A. We have child 1 pointer that is F1, child 2 pointer that is G, and child 3 pointer that is H. So it all runs on what? It all runs on linked list. Okay, so linked list is a very common and very basic approach which we follow to implement this tree data structure in my code. So this was it about introduction of trees. Now there are different types of trees. That is a binary tree and a binary search tree. Binary tree and binary search tree are both different. So don't get confused over there. Now let's talk about binary tree and binary search tree in tomorrow's lecture in detail. Okay. So here, one last thing I want to add is the topmost node, that is the root node, will always be the lowest what level. Why is this lowest level? Like just imagine um, a real tree has what roots in the bottom of what? In the bottom of the surface. That is at the lowest level. So that is what is same. We are representing it over here. So our root will be our lowest level and our leaf will be our highest level. Okay, we could also call this as height. But when we call this as heights, our root will be at height h1 instead of what L0. That is, this is level 0. But this is height 1 and this is height 2. This is height 3 and this is height 4. But for levels, it starts from 0. That is level 0, level 1, level 2, level 3. For heights, it does not start from 0. Height 1, height 2, height 3 and height 4. Okay.
Okay.
So this was about introduction to trees and this was it about hashing. Okay.